So we studied the convergence of series. Okay, we looked at so many tests to know when a given series will converge. And now it's paying off because we're going to approach the topic of a power series. Okay, and we'll start with a definition. Okay, a power series is an infinite series of the form that you see there. Okay. If we expand, we could write it out this way. And this goes on for infinity, okay? And what distinguishes it from typical series is you got a variable there. This x is considered a variable. A is a real number called the center, and ck are constants called the coefficients. And we have x as a variable. And that's the only thing I will say for now with regards to what a power series is. I believe it's important in mathematics to have motivation for why you're going to learn about something. And right off the bat, one may wonder, what's the use of a power series? Why would we care about something like that? And the answer is that you can approximate many functions with what's called Taylor polynomials. And so let's see how Taylor polynomials work. Okay, so we're going to motivate the topic of power series and then pick up more about power series. But first we'll take a look at this important topic of Taylor polynomials, which will give us a hint on why we should be studying power series. So suppose we want to approximate a given function with an nth degree polynomial. Okay, so we want to write this function as approximately equal to this p sub n, where n is an nth degree polynomial, and we write it out similar to what we have above there. So we're approximating it near this point a, so we have these x minus a terms, and we keep raising the power up till we get up till n. Okay, and notice that if we want to do this approximation and we plug a in, okay, once we plug a into pn, look at what happens to all these terms. So then it's a good idea then to have a matching condition that c naught, okay, which is the only term that would survive once we plug a into pn, it should be equal to fa. We should set that polynomial equal to fa to get an approximation. Well, then we could take a derivative of the function, and then we could take the derivative of that polynomial pn. And notice all the exponents will get taken down. You get a factor of n drop down when you take the derivative. The c naught term doesn't survive the derivative. Instead, you just get a c1 now. Now we do the same thing. We plug a into the first derivative of f and the first derivative of the polynomial, and we get this following matching condition. So it's a good idea to set c1 equal to f prime a if you want to get a good approximation. Well, we then take the second derivative. Okay, once we take the second derivative, again we have this now 2ct. This term is this 2ct comes from what's left when we take the derivative of that first term. The c1 doesn't survive the derivative, it's a constant. And we end up with, we could again plug a into pn, and the second derivative of pn, and we get this only 2c2 term surviving. And so it's a good idea to set c2 equal to f double prime a over 2. Okay, the second derivative of f at a divided by 2. All right, let's continue. And now we'll take the third derivative. And again, notice what term survives. So this 2c2, the derivative of it is 0. Then we get this term surviving, 3 times 2 times c3. This 3 times 2 came from repeatedly taking derivatives. Okay. And you might be guessing now, well, instead of writing 3 times 2, just write 3 factorial, right? And that would not be a bad idea. We now introduce this arbitrary kth term, and as we're taking more and more derivatives, we get more and more factors. The 2c2 does not survive. You get 3 times 2c3, so 6, or 3 factorial times c3. Plug in a into the polynomial approximation and into the third derivative of f, and you should set c3 equal to the third derivative of the function f at a. Okay, a is being plugged in after taking the third derivative. Okay, after you take derivatives, you plug in a, and you have this 3 factorial term. In general, so we're getting the pattern here. You take the kth derivative, and you will get this first term there, and the rest of these would have an x minus a, so that when we plug a into them, we get 0. We'll get 0 in all these terms except for that first term, which we could write. It's k times k minus 1 times k minus 2 dot 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 all the way to 2. Well, that's k factorial. Okay, that's k factorial. And so you want to, these terms will be 0, and so you'll have this f, the kth derivative at a is approximately equal to k factorial ck. And so it's a good idea to set an arbitrary coefficient, the kth term, to the kth derivative of f evaluated at a over k factorial. And you continue on all the way till you take n derivatives. Once you take n derivatives, it's a good idea to set that Cn equal to the nth derivative at a over n factorial. Okay, these are called matching conditions. These ck, c3, c2, these are called the matching conditions, and they'll give us a good approximation for f, for decently behaved functions. And let's go back to this power series. This power series doesn't stop at n. It goes to infinity. And one could imagine that for decently behaved functions, the more n, the larger n is, the better the approximation will be. And that would not be a wrong observation there. Okay, that would be the right observation. And so that's why we are studying power series, because eventually we will take that limit as n goes to infinity. And there, we're dealing with what's called not a Taylor polynomial, but a Taylor series. Okay? But the idea of Taylor polynomials gives us a motivation for why eventually we should take this limit as n goes to infinity. And so let's look at this formal definition. Let f be a function with these derivatives all the way to the nth derivative defined at a. The nth order Taylor polynomial for f with its center at a, denoted p sub n, has the property that it matches f in value, slope, and all derivatives up to the nth derivative of a. That is, we get these matching conditions here. Okay, that's how we found the coefficients, by using these matching conditions. Okay, so we used it, for example, over here. This was the matching condition once these other terms were 0, and we got C3 to respect that matching condition. The nth order Taylor polynomial centered at a is written this way. Okay, and rather than having a C naught there, we solve for what C naught should be, and what C1 should be, and what C2 should be. Okay, CK and CN. And more compactly, we could write this way and just give a formula for CK. So let's look at an example. Find the Taylor polynomials of order n equals 0, 1, 2, and 3 for the f of x equal to e raised to the power x centered at 0. Okay. And for b, we're going to use these polynomials to approximate e at 0.1 and e at negative 0.25. and check how good these approximations are with the absolute error. So A, we're going to take A equals 0 because that's where we're centered. So we're going to take A equals 0 in the formula above. And the exponential is a super nice sort of function to deal with because all kth, no matter how many derivatives you take, the derivative of e to the x is always e to the x. And so the kth derivative is going to equal e to the x. And we evaluate these derivatives at our center, so at 0. And so you have that the kth derivative at 0 is 1 for all k. So that's really nice. And using our formula for ck, again, a is at 0, and so we'll get e to the 0, which is 1. We found that there, over k factorial. This k factorial comes from that formula. Okay? And so the pth, the 0th polynomial, you just have that first term, f0, and that's equal to 1. So that's there. When you want to take the polynomial of the first degree, you'll have just these first two terms, and so that's what we're getting over here. And we have the x minus 0, so we just get x. Continuing on, now this 2 factorial shows up. And we have the x squared, and continuing on, we'll have that. That's the third degree polynomial, third degree Taylor polynomial centered at 0 for the function e raised to the power x. In general, if we took the nth degree, we would have this formula here, and we stop at n. Okay. Let's take a look at using these approximations. So we want to evaluate e to the 0.1. Well, that's just x being set to 0.1 there. So we have Pn at 0.1. So we plug in 0.1. And the 0th gives us just 1 for that. But the nth, when n is increased, so say up to 3, so that we're using this function there, and we plug 0.1 into this function here, we get that value. Okay. If we compare this with the actual value of e to the 0.1, and we subtract those two and take the magnitude, well, we get 4.25 times 10 to the minus 6 when we just take 3 terms. So it's a pretty good approximation for many purposes. What about a negative 0.25? Okay. Again, we could plug negative 0.25 into, say, the third one and get this. If we plug it into the second degree polynomial, we would get this, and on and on. And notice here that the error is significantly greater. It's still fairly small for many purposes there, 10 to the minus 4. But it's about 2 orders of magnitude greater than the error for 0.1. And one may wonder, why did that happen? Well, you're farther away from the center. Okay, 0.25 is farther away from the center. Okay, it's greater than twice the distance away from the center than 0.1. And so that's a typical rule. That's something that will typically happen there, is that as you move farther away from the center, the approximation with the Taylor polynomial will get worse. Okay, so if you're going to be near a certain value that you want to make approximations for, then it's a good idea to choose that to be the center. Okay, with all this talk about the approximation and how good is it, it's a good idea to define what's called the remainder. So let Pn be the Taylor polynomial of order n for f. The remainder is this. Okay, so this is basically how bad the polynomial approximates f. Okay, so it's f of x, the actual function that you're approximating with a Taylor polynomial, minus the Taylor polynomial. Okay, and we have a really important theorem here Taylor's theorem. Let f have continuous derivatives up to n plus 1 on an open interval I containing a, the center. For all x in I, f of x is equal to Pn, so the nth degree Taylor polynomial, plus Rn, the remainder. Okay, so you could write f of x as equal to the Taylor polynomial plus the remainder, where Pn is the nth order Taylor polynomial for f centered at a, and for some point c between x and a, the remainder is. So why Taylor's theorem is important is because we actually could ground what we're missing by approximating with a Taylor polynomial. Okay, there is a remainder. In that remainder, here we have a concrete expression of what the remainder is. And for some point c, now Taylor's theorem doesn't specify how to find c, but it does tell us that for some point c between x and a, x is where you want to evaluate the function or Taylor polynomial. So some arbitrary variable x. But for some point c between x and a, the remainder is given by that formula there, where you have the n plus first derivative of f evaluated at this c, which we don't know where it is, but we do know that it is between x and a, over n plus 1 factorial times x minus a n plus 1. Okay? And it might seem weird, if you don't even know what c is, you can't, have some formulaic way of finding it, then what's the point of having that remainder term and quantifying it this way? Well, this next theorem will help us. Let n be a fixed positive integer. Suppose there exists a number m such that n plus first derivative of f evaluated at c is strictly less than or equal to m. Okay? So you might not know c, but you do know it's between x and a, and you can find a bound on this term here. For all c between a and x inclusive. Okay, so for any c, we don't know c, but we do know it's between a and x, and we could bound it. The remainder in the nth order Taylor polynomial for f centered at a satisfies the following inequality. And now this is very important because you have a bound on your error. Okay, so anytime you're dealing with things numerically, you always want bounds on the error. Computers are finite machines at the end of the day, right? They can't express an infinite array of decimals or whatever. So you always got to stop the computation somewhere. And we'd like to have some way to quantify, what was the amount of error that we're getting from stopping. So let's look at this example. So use a third order Taylor polynomial to approximate the square root of 18 and find an upper bound on the remainder when using P3 to approximate root 18. All right, so we are approximating, we want to get square root of 18, so it's a good idea to choose f equal to the square root, and then we could plug, so what we're after really is f of 18, right? That's what we're after. Now, where do we want to center this? Okay, what center should we choose for our Taylor polynomial where we're going to approximate the square root of x? It's, one may think, let's do it at 18, but it turns out to be defeating, self-defeating to choose 18, because then you're going to need to know the square root of 18. Okay, that'll be your 0th term, and so it's a total waste of time. Do it at 18. What about 17? It's close enough, right? And we're choosing a center, and we're going to plug 18 at the end, and so we do want to stay close to the center. Well, 17 doesn't really have a nice square root. And again, why are we even doing this? Because we don't have a calculator, right? We're doing this stuff numerically. We don't need a calculator to know what the square root of 16 is. The square root of 16 is 4, okay? So that's the sort of closest center we could choose to the point where we want to evaluate, which is 18. And we do know the square root of it. Okay? We know it by hand, and we don't need to do any numerical analysis there. So we're going to choose to get the Taylor polynomial square root of 16 centered at a equals square root of x centered at a equals 16. Okay, and we just run through the mill here. Is f of 16 is 4. Square root of 16 is 4. We take the derivative. We get that. We plug 16 into this derivative. We get 1 over 2 times 1 over the square root of 16, which is 1 over 8. Okay, and again, that's showing you why we use 16. It helps us a lot. We take the second derivative, we get this, we plug 16 into that, and notice here something important. We always plug in the value, the center, after taking the derivative. And notice we're plugging in the center and not 18, okay? So we do this, the third derivative, and we get that value there. And so our third degree polynomial is written out this way. So we found, the coefficients will equal the derivative evaluated at 16 over, the factorial quantity. And so we get that polynomial, which we could write out after simplification this way. Okay, and so there goes our third degree polynomial. Okay, so we want now a bound. So we would just plug in 18 there into the that third degree polynomial, and we'll take a look at that in just a second. We'll know how much it's bounded. Okay, so we got a way to estimate the square root of 18, and now we want to make sure that our remainder is not so bad. So our error is not so bad. Well, we take a look at this theorem. We do have a bound m x minus 16 raised to 3 plus 1, because n is equal to 3 here, over 3, because n again is 3 plus 1 factorial, because n is equal to 3. And now we want our 3 at 18. Okay, that's what we're doing here. We want the remainder at 18, and so that's why that 18 was plugged over here. And we get this bound. Now what is m? M needs to be the upper bound of the n plus 1 derivative at c. Well, let's take the n plus 1 derivative. Here n is 3, so we'll take the fourth derivative and plug in c. So we'll take the derivative of this term here, plug in c, and we get this value. Now, how large can this term grow? Okay. Again, we're looking at from x to a. A here is 16. X, as far as we want to go, is 18. Okay, that's how far we want to go. So c is within the interval, inclusive 16 to 18. And so this term here reaches its max in this interval at 16. And so we plug in 16. That's as large as the fourth derivative can go in this interval. The interval from x equals 18 to c equals 16, right? Or c equals 16 to x equals 18. And we end up with this bound over here. We will choose m equal to this, and we'll get that bound there. So plugging in 18 into the third polynomial will give us the value of the square root of 18 up to an error of 3.8 times 10 to the minus 5. Okay, so that's just how bad we could do if we take the third. And it could be less than this, but not more. We have a bound on it. And so that's why this is useful. That's why Taylor polynomials are important. And that's why we're studying power series and their convergence. Because ultimately, we will be representing approximations to functions and functions themselves with infinite series.